Hello everyone, welcome to Basic Electronics Tutorials. In this video, I am going to discuss on the topic Enhancement Mode MOSFETs. Before I begin with the Enhancement Mode MOSFETs, let me provide a brief introduction to MOSFETs first. Please note, in my previous video, I have discussed about the construction and characteristics of junction field effect transistors. You can watch that video as a prerequisite to this video by clicking on the link shown in the top right corner right now, or I will leave the link of the same in the video description below. Coming back to this video, another type of the field effect transistor that has become most famous is the metal oxide semiconductor field effect transistor, which in short is for MOSFET. MOSFET is a type of field effect transistor that is commonly fabricated by the use of controlled oxidation of silicon. Very similar to a JFET, a MOSFET also has three terminals. They are called source, drain and gate. MOSFETs are broadly categorized depending upon the presence or absence of the channel into two types. The first one is called the enhancement type MOSFET and the second one is called the depletion type MOSFET. The only difference between these two types of MOSFETs is the channel. In a depletion type MOSFET, the channel will already be there, whereas in an enhancement type MOSFET, we have to create the channel by applying voltages to the terminals of the MOSFET. Further, each of these MOSFETs, that is both enhancement as well as depletion, are further categorized depending upon the type of the channel as N-channel MOSFET and P-channel MOSFET. Figure 1 here shows the symbolic representations of all of these MOSFETs. Starting with the top left MOSFET symbol, note that this is an enhancement type MOSFET. So, the channel does not exist. If you come to the same N-type channel but for the depletion type, please note this line here. This line indicates the presence of the channel and that is why the drain, the source and the substrate are connected together. The same can be said for the P-channel enhancement and depletion type MOSFET. If you look at the depletion type MOSFET, you can see that the drain, the source and substrate are connected using one single line, whereas in an enhancement they are not connected together, indicating that a channel has to be created for an enhancement type MOSFET, whereas for a depletion type the channel already exists. In this video, I will discuss the construction and working principle of a N-channel enhancement type MOSFET. Let me start the discussion with the basic construction of the N-channel enhancement type MOSFET. Figure 2 shown here represents the basic construction of the N-channel enhancement type MOSFET. A slab of P-type semiconductor material forms the base of the structure and this is referred to as the substrate. So, the substrate is made up of P-type semiconductor material. The substrate may be internally connected to the source terminal or a fourth terminal which is represented by SS here can be used for externally controlling the voltage level of the substrate. Further, two N-type doped semiconductor regions are etched within the slab of the substrate and they form the drain and source regions. These N-type doped regions are connected through the metallic contacts to the source and drain terminals. Please note there is an absence of channel between the two N-type doped regions. This is the primary difference between the construction of a depletion type MOSFET with respect to an enhancement type MOSFET. Lastly, a silicon dioxide layer isolates the gate terminal from the P-type substrate. This silicon dioxide layer is shown here with crossed lines. Please note, very similar to a JFET, a MOSFET also has the same three terminals, which are drain, source and gate. Well, that completes the basic construction of an N-channel enhancement type MOSFET. Let us now move on to understand the operation and characteristics of this MOSFET. To understand the operation of the N-channel enhancement type MOSFET, let us analyze the behavior of the device in three different conditions. Case 1 is the scenario where the gate to source voltage is 0 volt, but the drain to source voltage is a positive value, that is, it is greater than 0 volt. In case 2, the gate to source voltage is considered a positive value and the drain to source voltage is also a positive value. Here, both VGS as well as VDS are variables. Lastly, in case 3, the gate to source voltage is greater than 0, but it is a fixed value, that is, it is positive but is a constant, whereas VDS is greater than 0 and is a variable. Let us now understand the behavior of the device under these three cases. Let us start the discussion with the case 1 first, which is for the condition gate to source voltage is 0 and drain to source voltage is greater than 0. Since this is an enhancement type MOSFET, the absence of the channel will cause the device current to be effectively 0 if the value of the gate to source voltage is 0. Please note, the gate to source voltage is required to create the channel. Since the gate to source voltage is 0 here, the channel is not yet formed and therefore, the value of the device current, which is ID, is 0. Since the device current is 0, the device is said to be effectively in the off state. So, we understand that the device will not conduct until a channel is created between the drain and source regions. And to create the channel, we shall now use the gate to source voltage, and this takes us to case 2. The condition for case 2 is that the gate to source voltage is greater than 0 as well as the drain to source voltage is greater than 0. Let us consider the figure 4 shown here. Note that both the drain to source voltage as well as the gate to source voltage are greater than 0. Therefore, the drain and gate terminals are at a positive potential with respect to the source, which is connected to the ground. Let us recall the fact that like charges repel each other. Since we are applying a positive potential to the gate, the positive charge carriers, which are just below the silicon dioxide layer, will be pressurized to move away from the region. This is what is shown in this part of the diagram. I am going to repeat. Since like charges repel each other, applying a positive potential to the gate terminal will create a pressure to the positive type charge carriers, which are next to the silicon dioxide layer, and these positive charge carriers will now move away from the silicon dioxide layer. When these positive charge carriers move away from the silicon dioxide layer, this results in the creation of a depletion region just below the silicon dioxide layer. This depletion region will be void of any charge carriers. However, at the same time the positive charge carriers are moving away from the silicon dioxide layer, the electrons in the p-type substrate material, which form the minority charge carriers in the substrate, will be attracted to the positive gate voltage, and now they move in the opposite direction to that of the positive charge carriers. Since the positive charge carriers are moving away from the gate material, the electrons will move towards the gate material, that is towards the silicon dioxide layer. These electrons will now accumulate just below the silicon dioxide layer, creating a channel. It should be noted that the presence of the silicon dioxide layer and its insulating properties will prevent the negative charge carriers, which are electrons, by being absorbed by the gate terminal. So, all these negative charge carriers, which are electrons, will get accumulated just below the silicon dioxide layer, and therefore, a channel is now created between the drain and source. As the magnitude of the gate to source voltage is increased, the concentration of electrons near the silicon dioxide surface also increases. Once a channel is created, this supports the flow of charge carriers between the drain and the source. The value of the gate to source voltage VGS at which the channel is created between the drain and source is called as the threshold voltage and is denoted by the symbol Vt. It should be noted that since the channel was non-existent at the beginning, that is when VGS was 0, and is created or enhanced by the application of a positive gate to source voltage, this type of MOSFET is called as enhancement type MOSFET. If the value of the gate to source voltage is increased beyond the threshold voltage of Vt, the density of charge carriers in the channel will also increase, which results in an increased value of the drain current Id. Please note, the drain current is also considered as the device current. So, we understand that a N-channel enhancement type MOSFET is turned on when the value of the drain to source voltage is greater than 0, as well as the gate to source voltage is greater than 0. This voltage combination should be maintained to make sure the device turns on and starts conducting. Let us now move on to the last case where the gate to source voltage is greater than 0, but is a constant or a fixed value, whereas the drain to source voltage is greater than 0 and can be varied. To understand the behavior of the device, let us consider the figure shown in figure 5 here. As I said, let the value of VGS be greater than 0 volt, but is a constant. And the value of VDS here is assumed to be greater than 0 volt. Please note, in my previous video, when I was discussing the characteristics and construction of a junction field effect transistor, I have discussed about the pinch off process. I will be once again using the same concept here. So, I once again recommend you to watch that video for more information on pinch off. Coming back to this discussion, let us understand what is the behavior of the MOSFET when the gate to source voltage is greater than 0 and is a fixed value, whereas the drain to source voltage is allowed to increase indefinitely. To understand the behavior of the device in this scenario, let me take a simple PN junction diode into consideration. Let me now reverse bias this PN junction by connecting a battery. So, the p-type semiconductor material is connected to the N terminal of the battery, whereas the N-type semiconductor is connected to the p terminal of the battery, which is the positive. Let us assume this is VA, which is applied voltage. Since we have applied a value of negative voltage across the PN junction, the width of the depletion region has now increased. If I now increase the value of the input applied voltage, then the width of the PN junction will now once again increase. This is the effect of a reverse voltage applied across a PN junction. If I keep on increasing the value of VA, then the width of the depletion region between the P and N-type semiconductor materials will keep on increasing. This is a very important characteristic of a PN junction. So, we understand that increasing the reverse applied voltage across a PN junction increases the width of the depletion region. Let us now apply this concept to the MOSFET in consideration. If you look at the drain terminal, it should be noted it is connected to the positive potential of the battery. You can see at the VDS here, positive plate of VDS is connected to drain, negative plate to the source. Coming to the drain semiconductor region, please note it is made up of N-type semiconductor region. So, you are now connecting positive potential to the N-type drain semiconductor region. If you now look at the p-type substrate, you will note that the substrate terminal is connected to the negative terminal of VDS. So, we say that the N-type drain region is connected to the positive terminal of VDS and the p-type substrate is connected to the negative terminal of VDS. So, the PN junction between the N-type drain and the p-type substrate is reverse passed. Let me now apply the concept of increasing depletion region width to the depletion region between the drain and substrate. If I now hold the value of VGS as constant and increase the value of the drain to source voltage VDS, then the depletion region near the drain will start to widen. You can see that at this part of the diagram. As the depletion region width increases, the effective channel width will start to decrease. You can see the channel at the source it is wider, and as we move from the source towards the drain, it becomes more and more thin. This decreasing channel width offers a higher resistance to the flow of charge carriers between drain and source. Because of this, the charge carrier density between the drain and source increases. Eventually, the drain current will reach a saturation level very similar to that in a JFET. This process is called as pinch off in a MOSFET. I am going to quickly once again repeat the process. If VGS is greater than 0 but is a constant and VDS is also greater than 0 and is a variable, then because of the increasing reverse bias voltage applied between the drain N-type region and the p-type substrate material, the depletion region between the drain and the p-type substrate will start to increase. You can see that in this portion of the diagram. Since this depletion region width is increasing, this will cause the effective channel width to decrease. As you can see, the channel width at the source is quite higher than that towards the drain. This decrease in the channel width offers a higher resistance to the flow of charge carriers, and therefore, the carrier density increases. Eventually, the drain current will saturate to a value called as the drain saturation level, and this overall process is called as pinch off. Let us now apply Kirchhoff's voltage law to the terminal voltages of the MOSFET. So, I can write the voltage between the drain and source terminals, which is VDS, is simply the sum of the voltage between drain and gate terminals plus the voltage between gate and source terminals. Let me rewrite this equation for the voltage between drain and gate. So, this will be equal to VDS minus of VGS. Let us assume that the gate to source voltage is equal to 8 volt. And coming to the VDS, let VDS be now increased from 2 volt to 5 volt. So, there is a 3 volt increase. So, let us understand what happens to the drain to gate voltage when this happens. So, I will say VDG1, which was at 2 volt, is equal to VDS, which is 2 volt, minus of VGS, which is 8 volt. So, this is equal to minus 6 volt. Let me now compute the same once again for 5 volt drain to source voltage. So, VDG2 is equal to VDS, which is 5 volt, minus of VGS, which is 8 volt. So, this is now minus 3 volt. So, if VGS is held fixed at some value and VDS is increased to a new value, then the drain to source voltage will increase, and at the same instant, the gate terminal will become less and less positive with respect to the drain. Please note, when VDS was 2 volt, the drain to gate was at minus 6. That means the gate was at 6 volt. When we increase the drain to source voltage to, let us say, 5 volt, now the drain to gate voltage has reduced to minus 3. So, the gate now is at plus 3 volt potential. So, we understand that increasing the value of the drain to source voltage decreases the positive potential at the gate. This is a very important point to note. I am going to repeat. increasing the value of the drain to source voltage decreases the positive potential at the gate. Now, let us come back to the channel. When we were discussing case 2, we understood that the channel was created because of a positive potential applied across the gate. Now, by increasing the drain to source voltage, the potential at the gate terminal is now reducing. So, the channel which was formed by the electrons because of the attraction force by the positive gate will now lose that attraction force, and slowly they will start to move away from the silicon dioxide layer. If the value of VDS is now kept increasing, then the gate will become less and less positive, and this causes the electrons in the channel to move away from the silicon dioxide layer and pinch off would occur. This situation is called as the saturation condition. When saturation occurs, the value of the ID is equal to the drain saturation current IDSS and is a fixed value. Once MOSFET enters saturation, any further increase in the VDS will not affect the drain current until the device is subjected to breakdown conditions. So, to summarize, when VGS is greater than 0 and is a constant, and VDS is also greater than 0 and is a variable, we will find that the channel width keeps on decreasing as the value of VDS is increased until the device reaches a condition called as pinch off, where it simply saturates and the value of ID under such condition is equal to the drain saturation current and is a constant. Figure 6 here indicates the drain characteristics of the N-channel enhancement type MOSFET. Let us consider the condition where the gate to source voltage is plus 8 volt. As you can see from the graph, when VGS is equal to plus 8 volt, the MOSFET will enter saturation at this point, which is at plus 6 volt. So, we understand that one way of finding the drain to source saturation voltage is by using the graph. Another way of determining the drain to source voltage at which the MOSFET will enter saturation is by using the equation VDS saturation equals VGS, which is the gate to source voltage, minus of VT. This equation will also produce similar characteristics. If I assume the threshold Vt as a constant, then we will note that higher the value of the gate to source voltage, the greater will be the saturation level for the drain to source voltage. For example, for VGS equals to plus 8 volt, we obtain the drain to source voltage saturation value as 6 volt. If I take the gate to source voltage, let us say as plus 6 volt, then the value of the drain to source saturation voltage will be less than 6 volt, which in this case is approximately 4 volt. So, we understand that higher the value of the gate to source voltage, higher will be the value of the drain to source saturation voltage. Let us now talk a little bit on the threshold value. Here, we are given the value of the threshold voltage for the MOSFET as 2 volt. So, for value of the gate to source voltage less than the threshold value, which is 2 volt here, the drain current of the enhancement type MOSFET is effectively 0. You can see that for VGS equal to VT, the drain current curve is exactly on the x-axis itself. If the value of the gate to source voltage is now increased to a value greater than Vt, let us say 8 volt, then as you can see from the graph, the saturation current, which is the drain current ID, will also increase from 0 milliamps to this exact value, which is 10 milliamperes. So, we understand that higher the value of VGS, higher the value of the drain saturation current as well. Another important thing to note from this characteristic curves is that the spacing between the levels of VGS increases as the magnitude of the VGS increase. As you can see, when VGS is increased from plus 4 volt to plus 5 volt, the width between the ID curves is now considerably lesser than when VGS is increased from plus 7 volt to plus 8 volt. This is another important feature of the drain characteristics for an N-channel enhancement type MOSFET. For values of the gate to source voltage greater than the threshold voltage Vt, the drain current ID is related to the applied gate to source voltage VGS by a non-linear relationship given by the formula K into VGS minus of Vt whole square. Please note the RHS here consists of a squared term, which indicates that the relationship between the drain current ID and the gate to source voltage VGS is nonlinear. Here, the term K is supposed to be a constant and is said to be a function of the construction of the device. It is generally given by the formula K equals ID on divided by VGS on minus of Vt whole square, where ID on and VGS on are the values of the drain current and gate to source voltage at any instant in the characteristic curve, and Vt represents the threshold voltage of the device. Lastly, let us have a brief discussion about the transfer characteristics of the MOSFET as well. Figure 7 here indicates the drain characteristics, which is shown towards the right side, and the transfer characteristics, which is shown towards the left side of the N-channel enhancement MOSFET. But please note, we have now set them side by side so as to describe the transfer from one to the other. Coming to the transfer characteristic curve, which is the left curve here, please note, as long as the value of the gate to source voltage is greater than the threshold voltage, the drain current is effectively 0. This is what we have stated in the drain characteristics as well. As the value of the gate to source voltage is now increased, the drain current ID will begin to flow at an increasing rate as per the equation ID equals K into VGS minus Vt whole square. Please note, this equation relates the nonlinear characteristics of ID with respect to VGS. Another important point that should be noted in these graphs is that while mapping the drain current values of the transfer characteristics from the drain current characteristics, only the saturation level values are taken into consideration. You can see these lines here. Well, with that, we come to the end of this video on enhancement mode MOSFETs. If you found this video to be informative, kindly like and share this video and subscribe to my channel for more tutorials on basic electronics. Thank you for watching. Have a good day.